In the previous module, we learned how to build a CQASM algorithm and run it on a Quantum Inspire backend using the QI SDK. A few of the advantages over using web front-end editor are more control over your code and program flow. The results of the algorithm can immediately be used in your Python program to analyze. Serious big algorithms are not easy to maintain in the web front-end. Advantages that come with your favorite IDE in combination with tools as versioning of your software. Furthermore, QI SDK comes with some extra functionality and possibilities that are not available in the online editor. These are the advanced topics. We will discuss a few of them in this module. The first topic is the ability of QI SDK to program quantum algorithms in 3 different ways. The first is via programming CQASM as we saw in the previous module. This interface is comparable with the way algorithms are developed using the QI web frontend editor. For the other 2 interfaces, we can make use of third-party software frameworks ProjectQ and Qiskit to build an algorithm. In this module, we will mainly focus on using Qiskit as it is the most widely used. Another possibility QI SDK offers is to run your applications synchronous or asynchronous, which means you decide to wait or not for the results when you send an algorithm to Quantum Inspire to be executed. We conclude this module with an overview of some other possibilities without diving into them too deep. As we saw in the module QI SDK installation, to make use of a third-party framework, we have to install the necessary packages next to the QI SDK package. When all packages are installed, we get the following context overview. Qiskit and ProjectQ are 2 quantum computing frameworks that allow other packages to be connected as a backend. QI SDK is able to operate as a backend for both Qiskit and ProjectQ. The backend mentioned here may be a bit confusing because up until now we use backend as a Quantum Inspire compute backend for executing our algorithms. Although a bit confusing, the terminology used is correct. The idea is exactly the same. The backend for these frameworks is responsible for running the quantum circuits and returning the results. QI SDK positions itself as a backend to be able to run the circuit on a Quantum Inspire backend and returning the results. At its turn, the Quantum Inspire backend is also responsible for running the quantum circuits and returning the results. The reason we need QI SDK to be installed as a backend and not directly link a Quantum Inspire backend to Qiskit and ProjectQ is because the language they talk is different. Under the hood, the QI SDK translates the user circuit created in Qiskit or ProjectQ to a corresponding CQASM program and sends this program to Quantum Inspire to be executed on the chosen QI backend. The result coming from Quantum Inspire is translated to a result that Qiskit or ProjectQ expects. In the next part we will show how a quantum circuit is built and run via the Qiskit framework. We leave ProjectQ for now because Qiskit is more widely used. In the Quantum Inspire repository, several examples for running algorithms via the ProjectQ framework can be found. Keep in mind that Qiskit is a very large software stack. It has many possibilities. In order to run the circuits built in Qiskit on the Quantum Inspire backend, it must be able to translate the Qiskit circuit to CQASM. When translation is not possible, QI SDK will report this. Sometimes an incompatibility can be resolved by adjusting the circuit a bit to the possibilities of the specific Quantum Inspire backend. In the previous module, we went through all the steps that were necessary to run a CQASM program via QI SDK. The steps for running a Qiskit circuit are the same, but are done a bit different. In this module, we will go over the steps faster. When more information is needed for a certain step, check the previous module for a more extensive explanation for each step. The steps are: initialize the Quantum Inspire API, The second is selecting the QI backend for running our algorithm, then execute the algorithm, and the last step is inspecting the results. We will show the steps with the same example algorithm as we used in the previous module, and that's the bell state. Initializing the API is not much different as with using CCASM. We need a valid authentication and optionally a project name. Via the project name, we are able to find back the algorithm and results in the Quantum Inspire web environment. The API is now initialized with an instance of QI, imported from the SDK Qiskit package. To initialize QI, call set authentication with parameters authentication and project name. Via the QI API, we can select the backend using the method getBackend. The parameter for this method is the name of the backend. In this case, we use QX Single Node Simulator. The next part is Qiskit specific. Here we specify 2 qubits and 2 classical bits to hold the results after measurement. Then we specify a quantum circuit using these quantum and classical registers. To execute the circuit, we first transpile the circuit to rewrite the circuit to match the possibilities for the backend. The transpile function may rewrite or decompose certain gates used in the circuit to use only gates that are supported by the backend. Also for hardware backends, possible topology issues are handled. The transpile function needs the circuit and the backend to transpile for, in this case our QI backend. Then we call run on the backend with 2 parameters, circuit and the number of shots. When the number of shots is not given, the default number of shots is taken, specified by the chosen backend. The return value of run is not the result but the Quantum Inspire job. To get the result for the job, we have to do an extra step. By calling result on QI job, we get the results when the job has finished. The method is blocked until the result is received. This QI result is not only data but an object with several methods. To get the probabilities histogram, we call getProbabilities and feed the circuit as a parameter. The circuit parameter here is needed to get a result for that specific experiment. Qiskit function often allow to specify 1 or multiple circuits as a list. Other interesting methods we can use on QI results are getCounts, getMemory and getCalibration. The latter one gets the latest calibration data and is only useful for hardware backends. The method getCounts will return the number of times each state was measured. The total equals number of shots, here 512. GetMemory will return the 512 individual measurement outcomes. We quickly show what results we see on the Quantum Inspire website for this circuit. A few details are different than what we saw earlier for a CCASM algorithm. The name of the experiment is Circuit 120, a generated name by Qiskit. A more descriptive name can be supplied when initializing the quantum circuit using the name parameter. The execution time here is the actual execution time on the simulator, not the total time between sending the algorithm and getting back the results. The results page shows the CCASM algorithm that is the equivalent of the Qiskit circuit. This is the result of the translation we mentioned earlier. Notice that in this specific case, the measurements in the Qiskit circuit are not translated into CCASM measurement statements. The reason is that it is possible to optimize certain CCASM algorithms in Quantum Inspire. The topic of optimization is beyond the scope of this module, but when optimization is possible, QI SDK takes care of it. Although the measurement statement is not in the CCASM algorithm, the results show what we expect. The attentive reader saw it earlier in the Qiskit example algorithm. Running the algorithm, this is sending it to Quantum Inspire, was done separate for getting the results. Because QI has limited backend resources, it queues all incoming algorithms. At busy moments it may take a while before our algorithm is scheduled and the results returned, especially for hardware backends. As an alternative for calling a blocking request for results, we could ask for results only after we first checked if the job has completed running. To do this, we get the jobs involved from the return value of the run method. As explained earlier, this can be one or more experiments. For each job, a structure where the field status is available. When the status is complete, we know we can get the results without waiting. With a little effort, we even can save the identifiers of our QI job and its experiments. These are the individual jobs in the QI job, and retrieve the results in a different run. Remember that when a job is finished, the results are stored in Quantum Inspire and can be retrieved by the user at any moment. In the previous module, we used the API method execute QASM to run the algorithm synchronously. This method waits for the job to end and returns the results. To run the algorithm asynchronously, the API has a similar method execute QASM async, which returns a job. The job has method checkStatus to check the status of the job and method retrieve results to get the results once the job has status complete. The topics we can touch in this module are limited. At this point, we think that the available documentation can help to access more advanced features of the QI SDK. The QI SDK technical documentation can be found at Reader Docs. The knowledge base on the website contains valuable information. For example, about optimizing algorithms, as we came across in this module. Also, extensive information about CQASM can be found there. For some advanced functions, communication with Quantum Inspire is needed. Interfacing Quantum Inspire is always done via an authenticated instance of the API. In the previous module, we created the API instance ourselves. When using Qiskit, we get the API instance by calling qi.getAPI. The API exposes methods to manipulate objects we saw before, like projects, assets, jobs, results, raw data, backends, and calibration information. With this, the QI SDK Advanced Topics module concludes. We learned how QI SDK positions itself as a backend of the Qiskit framework to enable running Qiskit circuits on a Quantum Inspire backend. We showed how to create a Qiskit circuit of a bell state, run it, and expected the results of the equivalent CQASM algorithm on the Quantum Inspire website. Although we didn't cover Project Q in depth in this module, the idea is the same. The documentation contains examples for running Project Q algorithms. Then we saw how to disconnect executing the experiment from getting the results. This may come in handy when it is busy and many people want to use the same resources simultaneously, especially when running algorithms on hardware platform, because hardware platforms are not easily scalable. At the end, we showed where documents can be found to explore other possibilities of the SDK API.